Okay, it's this. It's a kilogram second per cycle. And you might say, well, what the heck is a kilogram second per cycle? It's the same thing as a joule second per cycle. It's the same exact thing. You just like over here. What did you do? You took a 1 second, right? 1 second, 1 second, and every cycle you got this number amount of joules for every cycle, right? Every one of these cycles here, every one of these cycles here, all these cycles, right? So you got 1h joules here because you got one cycle. Here you got 2 cycles in the second. That's 2h joules. Here you got 3 cycles, so that's 3h joules. So this is the same thing. It's a kilogram second per cycle. You take a second, right? Here's a second, here's a second, here's a second, right? Each one of these cycles, right? Because you get 7.37 times 10 to the negative 51 kilograms per cycle. Kilogram per cycle. You take it, and that's from a second. This is a second, right? This is a second. This is a second. So what do? I got one cycle here, so that means I get 1 John Black H worth of kilograms. This is 1 John Black H, this is the kilograms you get. Every cycle is worth this much mass, okay? It's equivalent, you know what I mean, to the energy, right? So this one you would get one of these. That cycle there would weigh this. What about this here? This one has 2 cycles, so you get 2 of these. And this weight of this 1 second of photon energy or whatever gets twice the kilograms. This one gets 3 times as many kilograms. Just like when you're talking about a joule second, this gets 1h, 2h, and 3h. You're talking over here, you're talking about kilograms. You get 1h of kilograms, 2h of kilograms, 3h of kilograms. Now, you might say, well, I don't know this formula, and this doesn't make sense. Okay, but let's use your formula. E equals mc squared, okay? And what is E equals mc squared? Basically, it's E equals m E naught mu naught. But we're going to just throw that away. Let's just say it's E equals mc squared. I made 2 mistakes in this video series so far. The first one, right here. See how I have E equals mc squared equals this? Mass times E naught mu naught. That's wrong. It should be this. Okay? The E naught and mu naught should be underneath the mass or kilograms. Okay? And I want you to realize something too. This formula up here, right? If I take this formula here and I multiply both sides by E naught mu naught, I will have kilograms equals E and then these 2 symbols, right? That's what this is. That's what I used up here. And this is E equals mc squared. See, I used H, which was Planck's constant, which was joules second per cycle. And I ended up with kilograms second per cycle. But if I wanted to, right, I could have just put energy instead of using Planck's constant. I could have just used 6.6 times 10 to the negative 34 joules, put it in there, and it would came out with, instead of kilogram second per cycle, I would just have kilograms. Okay. But I want you to look at all 3 of these formulas, right? Here's 1, 2, 3. This is energy. This is energy. And this basically is energy too, because it's mass, right? It's equivalent energy, right? Look at all the formulas though. I'll have the permittivity, right? And permeability. Permittivity, permeability. Permittivity, permeability. Did you notice that? They all have it. Because that's what, energy, mass, that's what gives you your mass. That's what gives you your energy. That's what it's space-time, charge, same way charge, they're all interconnected with these 2 constants, okay? And Z, and remember, this isn't really resistance, this is impedance, right? Remember when I did the thing where I was like, look, when I rearrange it to here, and it's like this is ohms. It is ohms, but it's not really resistance.
Yeah, that wasn't just an analogy when I was talking about this being watts and, over amps squared, and then the Z was like the resistance. That was an analogy. That means it's similar, but it's not exactly the same. But anyways, you notice they all have those same permittivity and permeability, right? But I want you to notice what we did so far, right? First, we did the energy, right? We know H, we know how to get H from these formulas here, right? But we know what H is. It's one sine wave. It's one cycle of energy, right? If you have, this is, it's a joule second per cycle, right? These are all seconds. Here you got 2 cycles, here you got 3 cycles, here you got 1 cycle. Each one of these cycles, it doesn't matter if it's long like that or it's short like this or short like, it doesn't matter. Every cycle gets this amount of joules, okay? That's the quanta, right? That's the lowest quanta right there. So obviously I'm going to say that's the, what we all think of Planck energy. This is what we're talking about, or we should be talking about, right? The smallest energy from one photon, right? You can't get a half a cycle, right? So then we used E equals mc squared, and or this formula here, which is the same exact thing, and we wanted to see what would this energy, right? Because energy and mass is the same, right? E equals mc squared. They're equivalent, okay? They're not the same, they're equivalent. But we figured out this is the kilograms, right? 10 to the negative 51 kilograms. That's what this thing weighs, all right? If this was, if obviously it's a photon, it doesn't have any mass, blah, 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 blah. But if this thing had, if you had a piece of mass, right, in kilograms, and you wanted that piece of, mass to have the same exact energy as this sine wave, 6.2, this times this right here, right? Then it would weigh this much right here, okay? These are the same. This mass and this energy are the same. They're not equal, but they're equivalent, right? They're equivalent, right? And they're the smallest. I mean, it's a sine wave, man. You can't get smaller than that, right? So, now we're going to go into the length and the time, right? And when we do the length, we're going to use this formula, and I'm going to show you another mistake that I had in a previous video in this series, okay, that was about this. So even though I'm using these formulas like this, or these, even though I'm using them, I'm showing you that I'm using their formula too, okay? This formula here is their formula, showing us what this energy is, right? Just like over here. This E equals mc squared, I showed you, we used their formula to show that this mass is equal to this energy, okay? So I'm using their equations, right? And my equations, but they're the same damn equations, you know what I mean? We rearrange it to mass equals energy over c squared, right? Which is kilograms equals E over c squared. We put our joules in here, right? Our Planck energy, or the smallest energy, right? We divide it by the c squared, and we should get an equivalent, right? Because E equals mass, right? Energy equals mass times c squared. So that's what we're doing here, right? We're taking our energy, we divide it by that c squared, and these are our units that come out to end up being kilograms, right? And you get the same answer here, 7.37 times 10 to the negative 51 kilograms, okay? So this formula says the same exact thing as this formula, and both formulas are saying that every cycle has an equivalent weight of this right here. Every one of them, whether it's this cycle, don't matter. They all get just like the H thing. They get so many joules, and this many joules, right? 6.6 whatever times 10 to the negative 34. This is equivalent. These joules are equivalent to this weight. These kilograms, they're equal. They're the same thing. This
amount of kilograms has the same amount of energy as this, and this energy has the same amount of mass as this. They're equal. They're the same. They're both talking about what one sine wave. This one is talking about the energy one sine wave would have. This over here is talking about the kilograms that every cycle would have. You can't go smaller than a cycle, right? So this would be your Planck, John Black mass, right? The smallest mass you can have. This would be the smallest energy, right? The Planck John Black energy. This is the least amount of energy you can have. Now, what about the Planck distance and the Planck second? And then we'll plug all these. Once I get I get length, time. We already have mass and energy. Once I get all four of them, we'll plug them into this formula up here to see, are you getting a black hole when you have these, my Planck lengths and my whatevers, time whatevers? Do you get a black hole then? And if so, what, if this is the smallest thing, right, then why am I should be getting some kind of infinities over here on my math when I do my math, you know what I mean? All these should go to infinities, but they're not going to infinities. Why? Because they exist, okay? And all these units here for Planck, all they're telling you is that's the smallest you can see something. That's the smallest you can take a picture of anything, because if you have your light wave any more energetic so that you can see something smaller, you will make a black hole. That's all it says. It doesn't say that physics breaks down, okay? It doesn't say it's the smallest possible, distance. No, it's the smallest distance that you can look at or take a picture of, okay? This is the smallest energy. This is the smallest kilograms. Not these. These are, no. These correlate to what you can't see. The smallest, if you put that energy or that kilograms in this little length here, you will make a black hole. That's all it's saying. Okay, so let me talk about another mistake I made. These are his units, right? Planck's. These are my two. Remember, we just did the energy and the mass. They're both equivalent. They're both just one sine wave or one revolution, one cycle. Okay. Now, in the last thing when we were doing his Planck things, right, we did this formula, right? It's the escape velocity formula, and I made a mistake, so we're going to go over it again. And then I'm going to put my numbers into this to see where my Planck length is, because apparently everyone believes that this is the smallest length. You can't get, so I should have infinities or something happening here when I find my Planck length, right? So anyways, remember, this is escape velocity. We set the escape velocity at c so that it was a black hole. Then we squared both sides so that we can get rid of that square root. We end up with this. Then we times both sides by r, so we get this. And now we can either divide by c squared to get r, this formula, or we can divide by 2g and get this formula. Alright, so we're going to use this formula here, right? Now, when we did Planck's length, right, we plugged in these numbers for his equation, right, and then we put it into this equation too, and we came out with this length, 10 to the negative 35th meters, right? And then I said, well, this g, and I remember I said, I'm not sure what's going on here, but if you leave the 2 out, you get the same exact answers he got with his equation. If you put the 2 in, then you will get 2 times this. You'll get 3.232 times 10 to the negative 35th meters, which is basically the same number, but it doesn't correlate exactly, okay? And I was saying, well, this was a reduced g, right? When it's put into this formula over here, right, you can see we don't have any 4 pi in our force, our gravitational thing there, right? So this reduced g already has 4 pi divided into it. That's why I call it the
reduce g because it's reduced. We've divided a 4 pi into it, right?